Welcome to GDP's Game Engine and Framework Patterns 2019. My name is Felipe Bellini, and this is a video demonstration of Project 2, addressing the classes lectured by Michael Finney at Fanshawe College. Project 2 features game animations, commands, and Lua scripts. Before talking about the details of the code and functionality, let's take a look at our OpenGL scene and the animations completed for this project. In this video, I'll be discussing and showing examples of moving along lines and mathematical curves, rotating and scaling objects in 3D space, making objects follow other objects, easing animations, serial versus parallel animations, event-driven versus immediate animations, location-based triggers or bounding box events, groups of animations, Lua scripting, and camera tricks. Let's open and run Bell Engine solution on Visual Studio 2019. We should see a scene where some animations will start occurring from the moment the game runs, and some animations that will only occur once an event happens within the game. From where the camera is located, we can see all the animations in the scene. Use the WASD keys and the mouse to move around the scene. The first example, we can see the Scale 2 script in action. The sphere in the horizon will increase its size over time until it reaches a scale desired by the user. In addition to that, we can see the bounding boxes with F4 key. Let's run again to check other animations. Now pay attention to the T-Fighter here. We're going to see a Move To effect, Orient To effect, and also when the ship arrives to this empty bounding box in 3D space, the bounding box will rotate. That's the location-based trigger. Let's move on to the next set of animations. Now we're going to take a look at the Serenity moving here. So this is following a mathematical curve. It will orientate and then it will move along the mathematical curve until it reaches the helipad here. There's a different set of curves that you can follow, parameters such as control points, start and beginning, but we'll see more of that later in this video. Now we're seeing the shuttle using follow object. So the shuttle is following this steampunk kind of ship, and this ship will move once the Serenity reaches the helipad. So since Serenity reached, now the steampunk ship will move. Notice how the shuttle will orient to and follow the object. This is all written in Lua. the movement smooths out until it gets close to the thresholds that are put in by the user. Now I'm going to go over a couple of camera tricks that I developed for this project. We're going to open the level XML file. If you remember from past projects, the level XML file is where and how I define my scenes. So we can see right away here our camera node, which defines the cameras that we are using in this project. So a camera of type camera locked at means that the camera will be locked at a certain target, which is a game object, right? So it means that if I rotate the camera in 3D space, it actually means that I'm rotating the object and the camera is locked at the back of the object. So let's think back to our scene that I just showed you in the videos. We have one of the animations has the shuttle following the steampunk ship. So if I say lock camera at shuttle and then run our game, the camera should be positioned right at the shuttle, and we can see a sort of a first person view of the animation. So let's take a look. So here we have it. The camera is locked still to the shuttle. You can see that the nose of the shuttle is showing. It's an interesting trick to simulate a first-person camera. I can manipulate the eye position to tweak that a little bit, also if I need to. Okay, let's check another trick. So if I can tell the camera to follow a certain game object, and game objects can have animations, what happens if I attach that to the aim and then give the aim a follow animation? That means, in essence, that I just created a follow camera. Let's check this out. Here I'm telling the aim to follow the shuttle. So we can see that the aim is following the shuttle. And we have the smoothing, the easing effect that was in the project scope for that. And the interesting thing about that is, since the camera is locked at the back of the crosshair, then it will rotate as well. So you get a very nice and interesting animation here of a simulated follow camera. Okay, let's move on to the next topic. So I've been talking about animations a lot, but what are the animations for me in this project actually? These behaviors you just saw are comment groups which are really a set of generic Lua scripts that can be modified by the users via XML. There are no pure C++ commands hard-coded in my engine. C++ just provides some static functions that Lua can call. You can find all the Lua scripts inside the Assets and Scripts folder. Inside Game, Assets, Scripts, and then some of the Lua scripts that I wrote for this project. When I define a level, I also define the animations that it will contain. If you think about it, I can have a level that's just a cutscene, and could have a level transition script that will change a game level to a cutscene level after an event happens. So here in Notepad++, we can see the animations node. We can see that animations can be of type parallel, which means that all the scripts inside a certain animation will run at the same time. The animation can be immediate, which means that once the game runs, the animation will be fired, or that can be event-driven, which means that something needs to happen in order for this animation to be triggered. Check how the scripts are defined here. So every animation has a collection of scripts and has a delay. In case of parallel animations, the delay will be added to each start time of the scripts. And if it's serial, then there will be a delay in the beginning of the animation. For instance, if there's 5 seconds of delay in a serial animation, then the animation will take 5 seconds to start, and then it will start processing all the scripts in the collection. For this animation in particular, the T-Fighter animation is a parallel animation, and it has 2 scripts, Move to and Orient to. Since they are parallel, it means that when the T-Fighter is moving in the air, it will also rotate at the same time. An example of serial animation is the Serenity animation. It will first orient to whatever place it's going. Then once this is complete, once the duration ends, it will move to a follow curve script, and when that happens, it will trigger an animation for the steampunk ship animation. This is another script here. I will pass the name of second script, and then this script will run after all the other scripts have been completed. So the way that I designed the script is that they're generic in nature, and they only carry a set of parameters. It's a map inside the C++ code, where each of these parameters here are replaced during runtime in the Lua script. So if I say that the maximum speed is 1, then in the object follow object.lua, the max speed will be replaced by whatever number the user has put in the XML file. That's with the exception of the unique script name, for instance. This is generated automatically and during runtime. So you can see that there's no unique script ID here. So what will happen is that the path will become the name of the script, the unique script name. For instance, if the file is called object follow object.lua, this will be object follow object lua um, XYZ 1, 2, 3, 4, for instance. Inside the engine, we can find this in Bell engine here, projects. So scripts. So here's the scripts, here's the algorithm that I use to replace the parameters inside the Lua string. Because once I set the script, it will read the Lua file, create a name for it, and so on. And the animation, as I was telling you earlier, is a set of scripts that have triggers, type, and delay. And in code, this is all processed by this Lua animator class, which is a base class for the game Lua animator. The Lua animator is a modification of Lua Brain that was given by Michael Finney during class. So you can see a bunch of commands here, a bunch of methods that are used to update all the scripts. This is the level, so the Lua animator has knowledge of the current level that's running in the game, so it knows of all the game objects. In fact, the game Lua animator in our game, which inherits from this class, is a singleton, so there's only one in the whole game. We can see methods such as fire animations, which will handle animations accordingly to their type. We have our register functions here, which in fact allows the Lua framework to access C functions that are defined in this game Lua animator class. For instance, we have a bounding box check to see if an object has come in contact with the bounding box. It will really check if a point is inside the bounding box, and so on. For instance, there was the idea of when a script finishes running, when its duration has completed, the script can dispose itself. So the script can call this function here that will tell the Lua animator to unhook it from its map. So the script will die and stop appearing inside the update loop. An update is called inside my world class. So every time I call update in my world, I have the Lua animator update as well. There are two topics that was specifically required for this project, which are the mathematical curves and the easing functions. So I'll show you how that's being handled in my code. So I'm going over to the T-Fighter animation because I know that the move2 function has easing option. The easing option is a parameter that's an integer of value 7. Okay, so what this means is that 7 is a value for an enum type inside the code. So if I go over to the Bell engine and check the easing.h, we can see this enum type here. So all these functions are available to animators. They can do so many combinations with this. Cubic is in, cubic is out, is in and out, circular, sine, sort of easings, quartic, quintic. So there's a bunch of things that can be done with that. This will effectively be calling the functions within GLM, which is our math library. very useful for this project. And here we have a get easing value, which will handle the user input. And the same idea has been applied to the mathematical curves, for instance. So say Serenity uses the follow curve script that takes the curve option. So in a very similar manner, if we go to the curve class, we can see the enum where that value gets translated to. So we have the option to have a Catmull room, cubic, or hermit mathematical curves. So there you go. So effectively, get curve point and get easing value are functions that get exposed to Lua in the game Lua Animator, or better, they're used within the game Lua Animator thing. Another example of that is the smooth step, for instance. So in the follow object script, it calls the smooth step. That's from GLM. It's the same idea. That concludes our presentation. For more information, contact Felipe Bellini or Michael Finney at Fanshawe College. Thank you and happy coding!